Okay, so picking up on our virtual memory, we're at the point where we want to pick which the operating system is going to allocate a certain number of pages to our program. They could do it on a local basis, which is they give a certain number of frames to our program, and then we have to deal with that number of frames. Or they could do it at a global level, meaning if our program is running very slow, maybe they'll give us some extra frames, taking them from some other program, or it might do it on a per process basis. Okay, so what we're going to do is we're going to, well, we'll just kind of review where we left off last time. The operating system in this example has decided a particular page size, and then each of the pages are numbered from, starting at 0 until we use up all of main memory. So here's page 0, page 1, page 2, I'm just writing numbers in decimal. And here's the binary version of the page number. And then inside of these blocks is the data for that page. So we always start with the operating system, and then we get to a point where we have storage for your process. So the page table, let's say from the point of view of your program, you have at this moment, the operating system has given us 3 page frames to store our program. Our program has more than 3 frames, but the operating system has only given us 3 because, as you can see, other programs are running. Process B has a page here and a page here. Process C has some. It happens to be an empty frame, but maybe that's dedicated for some other process. So at this moment, virtual page 0, 1, and 4 of our program are located scattered throughout memory. And in our page table, we have our virtual page and our real page. And our real page in binary is 98. So I kind of wrote it out in decimal here. So we're basically saying that this page table points to this piece of storage. What we mean by pointing to it is we recorded the page number in binary. So page 0 resides right here of process A, or process A. Page 1 resides here. Page 4 resides in decimal number 100. So page 3 and page 2 are currently missing, and if there's a page 5 or page 6, they're also currently missing. So as our program is running, let's say we are running instructions right now out of page 1. So we run an instruction, then the next instruction might be right after it, the next instruction might be right after that. And then maybe we do a procedure call, and now we have to jump into page 2 of our program. So since we are going to a new page, we have to look in our page table, it's page 2 in memory, and at the moment it's not. And we've used up all our page frames. So we have to go out to the disk drive and bring in page 2 into main memory, because the processor can only execute out of memory, can't execute directly off the disk. And we have no room for it, so we have to pick one of these 3 pages to bring in page 2 and write on top of it, and then obviously we have to go update our table to say the new page is in. So, okay, so just a couple of side things. The operating system will allocate a certain number of page frames to each process. That might not be enough page frames to put the entire program in, but that's okay. We only need to have the pages that are currently, the instructions are being executed from. When the multi-level processing, the number of programs running at once, gets to be very high, the operating system is going to have less page frames for us to use. It's going to give out less to all of them. And this will dynamically change over time. If the operating system doesn't have many programs going, it could say, okay, here's some more frames for you. So, so let's say if the operating system is currently giving our process, as an example, 3 page frames, and currently the 3 page frames are occupied, we execute a line of code that is in a frame that's currently not in memory, then we need to go out to the disk drive, bring the page in, and therefore pick a page to remove. Now what we mean by removing is, we could, if the data in the page frame has not changed, we could just write the new page right on top of it. if the page happens to have like storage whose variables have been changing, and we want to take it out of memory, we'd have to take time to write the page, because it's been altered, back to the disk drive. And then we could put the new page on top of it. So that time might come into play when we're considering which page frame to take out. So let's say, for example, we're going to very possibly use what we'll call a page reference string. So suppose you're running some code, and initially the operating system gave us 3 frames, and since we're computer scientists, we always start at the number 0. So they give us frame 0, frame 1, frame 2. In the last example, those were, page 96, 98, and 100. So we start running out of executing lines out of page 0. So first thing we have to do is load page 0 of our program in, start running code. We start running lines. So there could be, 10 lines, 100 lines, all out of page 0. Eventually, we now start running lines of code out of page 1. So the first time we enter page 1, we have to bring in page 1 from the disk, update our virtual table. And now we have page 0 and page 1 in memory. There's no point in kicking page 0 out, because even if it's not going to be used for a while, it's here. There's no point in kicking it out, so we'll keep that around. So now we're executing some instructions, could be many instructions out of page 1. And now the next page we go into is page 2. So the operating system gave us 3 frames, so we load page 2 into our final empty frame. We update our tables to say page 0, 1, and 2 are in memory. And then we keep running some instructions out of page 2. Now page 2 makes a jump back to page 0. Maybe there was a big while loop in page 0 that ran through page 1, got to page 2, and now it's going back to page 0. Or maybe there was a function call. Page 0 made a function call to page 1, and page 1 made a function call to page 2, and now it's done, and now we're going back to page 0. But for some reason, we're now going to start running code out of page 0 again. So we look at our virtual table, and we find it's in memory, and we start running instructions out of it. Now our program, maybe page 0 is the main function, and it's calling procedures or functions that are all over the place. We're now going to run some code out of page 3. But the operating system, which is really our 4th page, but the operating system has only given us enough space to hold 3 pages. So we have to go out to the disk drive, get page 3, bring it into memory, and obviously we have to pick one of these 3 to basically kick out or write page 3 on top of it. So here's the question. Which one do you kick out? And does it even matter? Why would you put a lot of effort into picking a good one to kick out? But anyway, does anyone have any ideas just off the top of your head? Which one would you write it on top of, and why? So we have our program ran some instructions, could be 1, could be 1,000, out of page 0. Then we started running instructions, at least 1 out of page 1, then 2. Then we went back to 0, and now we're in page 3. So we have to load page 3 on top of one of these 3. Does it even matter which one to pick, or which one would you pick? It doesn't even have to be a good reason, just any reason.
And like, you don't have a lot of data to make that kind of decision, but if you were really reaching, you could do the right over number 1, because it's the farthest away of the least reference. So like zero's referenced 2 times, so it's used the most currently. 1 and 2 were both referenced once, and 1 was referenced before 2. So 1 is like the furthest away.
Okay, so out of all the ones currently in memory, the one that has been referenced, I guess the best way to word it is the most recent reference is the furthest in the past, right? Okay. Anyone have another reason you might pick a different? Any other reason you might pick a different choice to kick out or write on top of? Write the page on top. And why 0?
Because they just used it, so they might not need it anytime soon.
Oh, okay. Okay, is there another reason someone might pick 0? It's interesting you said that, because that's one of the algorithms and that operating systems use. But anyway, so you're saying because it was used recently, it probably will. Well, first of all, what are we trying to do? When we're trying to pick the one to kick out, what would be considered a good choice?
Something that will be called next.
In the near future, right? Basically, our goal is, if we could see into the future, and I kind of intentionally put the future down here, but if you could see into the future, you'd like to keep the pages around that are going to be needed in the near future. But generally, you don't know how your program's going to run, what the future is, or if statement's going to be true or false, and you don't know which way you're going to go. So a lot of times you don't get to see the future. But our goal is to try to say, let's keep the pages around that are going to be needed in the near future. And the only information we have is the past. So we're using the past to guess at the future. And so one thing you were saying was, since page 0 has just been used recently, it may not be needed in the near future. Interesting. So any other is some people say pick 0, but also for a different reason. Not that it's been used recently, but because it's been sitting in here a long time. So therefore, let it go. So okay, so there's different algorithms, but if you could just we'll revisit this algorithm. If you could see into the future, then which one would you kick out? And here we can. I showed you the future.
2.
You would kick out 2 because 0 and 1 are going to be needed very soon. If you could see into the future. Okay. So really, but I guess what we're trying to do is we're just trying to pick one of them to kick out, and the best one to pick is the one that is not needed in the future. And if you only know data from the past, what's the best one to pick? And the one that hasn't been used in a while, we could take a guess, that won't be needed soon. That could be a wrong guess, but we could do that. And then the one that's just been used might not be needed. We just used it, and now we're leaving it, so maybe it's not needed. Okay. So a couple of popular algorithms, page replacement algorithms operating systems use is first in, first out. So that would be the case where we say it doesn't matter how much is being used, 0 came in first, then 1, then 2, so we'll get rid of 0. Since that was the first one in, it'll be the first one to go out. So the other algorithm is last in, first out, which in the case of, last in, first out says since 2 was loaded very recently, then it probably won't be used in the future, which is somewhat similar to what you said. Yeah, you were going to write on top of 0, since it was just used, it probably won't be used in the near future. That would always kick out the most recently added one. The first 2 that come in kind of stay around forever. So last in, first out is when the number of frames you get, the operating system keeps changing them. It might have some effectiveness. Okay. And then the one that, our first suggestion is the least recently used one. Okay, so now for the operating system to implement these, for example, first in, first out, the method is to take the page frame that has been in main memory the longest amount of time and remove it. How can the operating system keep track of this? It could maintain a linked list. So every time a page comes in, you have a head and a tail of the linked list. Every time a page comes in, you add the new page to the end of the list, the tail of the list. And whatever the head is pointing at, that's the one that should go next. The new one comes in, gets added to the tail, and you just keep walking through the linked list. So you know from your data structures days how to keep a linked list. If you wanted to do last in, first out, you'd put the pages on a stack. So the one at the top of the stack, which is the most recently one to come in, that would be the first to go. And as the stack changes sizes, you would always pop the one on the top of the stack. So what's pretty popular with most operating systems is to try to use the least recently used element. So how could we implement this? So in our last example, we said we use page 0, then we use page 1, then we reference page 2, then we went back to page 0. Now we're going to kick one out. So the fact that we used page 0, even though we didn't load it in, we just used it again, we have to somehow update our mechanism for keeping least recently used. So what are some ways we could figure out at this point in time that 2 and 0 have both been used recently and 1 has not been used in a while, so therefore we'll kick that one out? What data structure can we maintain? Or what way can we keep track of that? So for first in, first out, every time a page is loaded, you put it on the end of your linked list. Every time a page leaves us, you delete it from the beginning of your linked list, then you maintain a linked list. That's how we can keep track of first in, first out. But if we want to update every time a page has been referenced, not just when it's brought in, but every time it's referenced, we have to update something. Say, oh, this one's now been used recently. How could, any ideas of how we can do that? So, two popular ways of doing it would be to maintain a linked list, but now, instead of updating the linked list every time a page comes in, every time a page is used, you have to go through the linked list and find that page, and then propagate that one to the end of the linked list. So the end of the linked list is who's been used recently, the beginning is the ones furthest away. And if you remember from your data structure, that would be a linear time algorithm, and you'd have to do that every time a page is run. So that could be time consuming. Another one is you could ask for the hardware to have a timestamp on every page. So every time you reference read or write from a page, you also update the timestamp simultaneously to it. Now when you go to pick out a page, which one gets to go, you now have to look at all the timestamps and pick the one with the oldest timestamp, which would also be time consuming. So maybe intuitively, the least recently used might be the best predictor of the future. But it does, the way you go to implement it is very time consuming. So approximations of it are popular. There's an algorithm sometimes called not used recently, which kind of by its name is a weaker version of least recently used. So we can have, with each page, we can have a bit that gets turned on. So when the page is loaded, its bit is 0, and then if you go and reference it, you turn the bit on. Now that can be done instantly. Every time you go to read or write the page, you turn the bit on. And then on occasion, we just go and shut the bits off, and then let pages get referenced again. So at a point where we go to pick a page to kick out, some of the bits are on, some of the bits are off. The ones that have a bit that is on is near, has been referenced somewhat in the near future. And one that has a bit off, we can just kick out the first one we find. So it's an approximate, and then if there's ever a time when all the bits get turned on, then we just shut them all off and start the whole process over again. So why would we use this instead of least recently used? Because this really approximates the one that's least recently used. It won't give us the one that has been least recently used, but it'll pick one that's been somewhat not used recently. And the reason is this takes less time to implement. Every time you read a page, you turn the bit on. Then occasionally, every once in a while, you shut all the bits off. And then if you touch a page, you turn the bit back on. And when you want to pick a page, you just go through all the frames you have, and the first one that has the bit off, you just pick that one. And you're hoping that's one that hasn't been used recently. Doesn't give a great answer to it, but it can calculate it fast. Then to maybe be a little bit more fair, you could use 2 bits. Turn a bit on when the page is referenced, occasionally shut the bits off, then when the page gets selected to be kicked out, if it's the first time it's ever been kicked out, you turn its second bit on, which gives it a second chance, and then go pick something else. So with 2 bits, you still have the high speed of turning bits on and off, and deciding which one to pick, but you're not going to load a page in, and then because it hasn't been used right away, it gets kicked out immediately. This way it will be given a second chance. So these are 2 algorithms that approximate least recently used, but take much less time to implement. Ideally, the optimal page replacement algorithm would be if you can see into the future. If you can see into the future, then you would know, leave the pages in that you're gonna need in the near future. If you can't see into the future, then after your algorithm, after your process finishes, you could then look back in time and see how good your algorithm ran compared to this. This would be a good benchmark. You could never do better than this. So the optimal would be the one where you look into the future and keep around the pages that are in memory. Okay, so an example of a page reference string. Consider a process in main memory where the operating system is given 3 frames. And we're going to have, for example, page 0 is going to be referenced, then 1, then 2, then 3, then 2, then 3, then 1, then 0, then 2, then 3. And we'll go through, each of the algorithms. So, for example, first in, first out, we're given 3 page frames. So we reference page 0, so we bring in page 0, and this X means we had to go out to the disk drive. So every time you go to reference a page and it's not in main memory, they call that a page fault. So you have to take a time out, go out to the disk drive, bring the page in, update your tables, and then your program can start running. While that's happening, the operating system will move another process onto the processor. So that can get some work done while you're out at the disk drive. So each one of these X's is how many times we have to go out to the disk drive. Going out to the disk drive takes a lot of time, so that's our goal, is to minimize that, get as few X's as possible. So we bring in page 0, run some instructions, then bring in page 1, another page full, bring in page 2, another one. Now we're going to bring in page 3. So where do we bring in page 3? If we're using first in, first out, we write it on top of page 0, because that's the one that came in first. So now we have 3, 1, and 2 in memory. We reference page 2. That's not a disk fault, a page fault, because we have 2 in memory. And then 3 again is in memory, then 1 is in memory. Now we have to reference page 0. We don't have any room for it. So out of 3, 1, and 2, we say which one's been in the longest. This one's been in since here. 1 has been in since here, 3's been in since here, 2's been here. So we write 0 on top of 1. That costs us, we have to go out to the disk drive to bring it in. And the rest of the references are in memory. So if we happen to do the same string using a different algorithm, the least recently used, page 0 comes in, 1 comes in, 2 comes in, 3 disk fault, page faults. Now 3 needs to come in. So we put that on top of 0, because that's the one that hasn't been used the least recently. Now we reference 2, we reference 3 again, we reference 1. There's no page faults along here. And now we need to bring reference page 0. So since we're using least recently used, we don't care when it was loaded. We look back in the near recent past, we say 1 and 3 have been used recently, so we'll keep them around. The idea is, since 1 and 3 have been used recently, then 1 and 3 will probably be needed in the near future. That's what our guess is. So we load page 0 on top of 2. So now we have 1 and 3, because they've been used recently, and 0, which is the new incoming page. And then we need 2, which means we made a bad guess. Right? We kept 1 and 3 around and kicked out 2, thinking 2 won't be needed in the near future, and it turns out it was. Obviously, I can just make these numbers whatever I want, but in this case, we had to bring in page 2. And since we were bringing in page 2, and 0 and 1 have been referenced recently, we kept 0 and 1 around and brought 2 in on top of 3. And then, of course, I asked for 3 right after. So with the least recently used algorithm, same reference string, same program running the same pages. We had 1, 2, 3, 4, 5, 6, 7 page faults. So this program would take longer to run because we chose a page reference, a page replacement algorithm of least recently used. So could we conclude from this that, well, first of all, let's just benchmark, see how bad these were compared to the best it could possibly be. The optimal one is every time you go to bring in a page, like here we're bringing in page 3, you look into the future and say, well, we need 2, we're gonna need 3 again, but 3's coming in. We're gonna need 2 and 1 in the near future, so let's keep them around. So we put 3 on top of 0. And this was okay, this was okay, this was okay. Now we have to bring in 0. So we look into the near future. We're gonna need 2 and 3 around, so we'll keep out of 1, 2, and 3, we'll keep 2 and 3 around. So we'll bring page 0 and put it on top of 1. And since we need 2 and 3, they're already there. So the best you could have possibly done is 5 page faults. There's no algorithm that could do better than looking into the future and keeping the pages around. Any algorithm that looks at the past to guess at the future couldn't do better than this. So could we draw a conclusion? Could we say first in, first out is better than least recently used? Because this string happens to, no, it just happened to be, right? And chances are the author picked that string to do this. Can an algorithm have less page faults than the optimal one, the one where you look into the future? Could you ever come up with an algorithm that could be better than that? No, that's the, yeah, that's why it's called the optimal one. Yeah, it wouldn't have that name. Okay, all right, so that's like a little, yeah, side discussion. Okay, so if an operating system had, let's just say for example, an operating system has 12 available page frames and there's 4 programs running at once, how many should it give to each? So you might think, all right, 12 frames, 4 processes, 3 each. Now why not? Give them all 3 each, see how they could do. Suppose the operating system is noticing that process 0, process 1, process 2, and process 3 each have 3 page frames, and it keeps track. Every time it goes out to the disk drive, it says, it keeps track of what percentage of the time, every time you go to a new page, what percentage of the time do you have to go out to the disk drive? So if you notice one process goes out 20% of the time, let's say 80% of the time the page it needs happens to be in memory, 20% of the time it has to go out to the disk drive. So that's going to slow that one down. Process 1 goes out 10% of the time, and 90% of the time the page it's looking for is in memory. So this is really like a program that seems to be like less erratic. It's not jumping around so much. Suppose the second one is also 20% of the time it has to go out to the disk drive to bring the page in. And the third one, you notice 50% of the time it's going out. So chances are this third program is jumping around a lot. Maybe it has big functions or big while loops or making big function calls that call other functions. They're really jumping around a lot. Would you stick with this rule of every program has 3 page frames? Or would you try something else? And is there any reason to try to balance frames? Or should the operating system make adjustments to how many frames each program has?
Take a frame from process 1, give it to process 3.
Okay, so what that will do is, so the logic is that this one will page fault more, because if you give it less frames, then when it goes out to go to a new page a lot more often, it will have to go out to the disk drive. And this one will do a lot less. Right? So using the theory, the more frames you have, the less page faults there are. Okay. And I guess so the net result would be, this one, if you didn't do that, this one would probably finish very quickly. Or who knows how long it is. But this could get a lot more work done in the same amount of time as this. Whereas you're being more fair. And also later on when we talk about queuing theory, by balancing this, taking a frame away from this one and giving it to this one, letting them run and recalculate these numbers to see if they come out even, we may have a situation where the processor is being used close to 100% of time. So that could be an improvement too. Okay, so the working set principle, we'll cover this more later on, of course, when we talk about queuing theory, but the operating system should try to manage all processes so that the processor is being used as close to 100% of the time as it could. Right? We never want to have a processor and it's sitting idle, because every program is waiting for something. Especially going out to the disk drive and waiting for something, then you have nothing to process. So the working set principle is the operating system should try to have each process have as many page frames as it can, so that at least one program at all times can be ready to run on the processor. Not stalled because it did a P function and it's waiting for something, and not stalled because it's going out to the disk drive. And then just one side comment. The idea of giving more page frames to a process, thinking it's going to have less page faults, is generally a true statement, but there is an anomaly to this. So you can Google the Ladys Anomaly. So the idea is when you're looking at, for example, the first in, first out algorithm, if you had 3 page frames and you happen to pick this string, it's an interesting string, a reference string, and counted up how many times you have to go out to the disk drive if you had 3 page frames, I put in red every time a page had to be brought in from the disk. So here we had 0 brought in, here we had 1 brought in, 2 was brought in. Now 3 needs to come in, and we're doing first in, first out, so we write it on top of. So basically we'll keep going like that down. So we'll write it on top of 0, then 0 wants to come in, so we write it on top of 1, then 1 wants to come in, we write it on top of 2, then 4 wants to come in, so we write it on top of 3. 0 is already in, 1 is already in, now 2 wants to come in, so it's going to be written on top of this one, 3 wants to come in, it's written here. So we have these page faults, 1, 2, 3, 4, 5, 6, 7, 8, 9. So as this is running, 9 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 9 out of 12. So we have a 75% page fault rate. So we say, oh, that's pretty high. And let's say some other program's running a lot faster, so we take a frame from them and we give an extra frame to this one. So what if this same reference string ran, but instead of having 3 page frames, you had 4? That should make us have less page faults, right? We should have less than 9. So if we had 4 page frames, we'd load 0 in, 1, 2, 3. So those are the first time you're loading them in. So that's expected. Then we reference 0, same as here, and 1. No page fault because we had that page in. Now we want to bring in 4. So in this one we had to bring in 4, plus this one we had to bring in 4. So still no improvement yet. And now in this one, we wanted to bring in 0, it was already there. But because we had 4 page frames here, when 3 came in, it came in on top of 0. And we got this far and we don't have 0 anymore. But this one, which only had 3 frames, just so happens to have 0 around. At such few frames that 0 came back in. 0 came back in on this one. So with 4 page frames, we actually had a fault here. We had to make room. Page 0 was not in memory, but in this case it was. So having the extra page frame actually caused us, for this particular string, an extra page fault. So we bring in 0, and now we ask for page 1, and 1 was also hanging around from the past when we only had 3 frames, but now it's missing. So we had to bring in 1. That's another page fault. And now we ask for 2. In this case, 2 had to come in here and 2 had to come in here, so this is no better. And then the last one we asked for 3 and we asked for 4. So the designer of the string was obviously trying to make the point that with first in and first out, there is a scenario where the operating system says, oh, this one's going too slow, too many page faults, let me give them an extra frame, and it actually makes things worse. So, but it's rare that this would happen. So we're still going to follow the theory if you're using first in, first out, if we give you an extra frame, it should generally help you. But it's just good to know, it could actually make things worse. So with this anomaly, could this anomaly happen with a different page replacement algorithm like least recently used? So let's just see, where, the first scenario where the issue happened was this one, this frame. With 3, we had 0, 1, and 4 in memory, but when we had 4 frames, we had, wait, I'm sorry. Yeah, we had 0, 1, and 4 in memory, but here we had, wait, this one, it's this one. Okay, so, yeah, when we had 1, 2, 3, and 4 in memory, and 0 was the next one that was being referenced, we had a page full. But when we only had 3 of them, we had 0, 1, and 4. 0 was in memory. So that's why 4 frames ended up being worse than having 3 frames. If we were using least recently used, could this same scenario occur? Could you have 4 frames? When you have 4 frames, you have a set of 4 frames. And when you have 3 frames, you have a page that's in here that's not in this set. Is that possible in least recently used? So again, for first in, first out, if you had 4 frames and you ran through the string in this order, you would end up with 1, 2, 3, and 4 in memory. But if you only had 3 frames, you would have 0, 0, 1, and 4. The difference being 0 is in memory, and here 0 is not in memory. And then 0 was asked for. Could that same scenario occur with least recently used? Could the 4 that you have here and the 3 that you have here, is it possible one of these would not be in that set? Because least recently used is,
For the, you mean for the 0?
yeah, is it possible the same scenario could occur? That with 3 frames, so really this anomaly occurred because when we had 3 frames, the 0 was in memory. But when you had 4 frames, 0 was not in memory, and then we asked for 0. And that's where we had 4 frames was worse than 3 frames. That would happen with first in, first out. But if we were using a different algorithm, least recently used, could you ever have the scenario where with 4 frames, you have a set of page frames, and with 3, you would have a page that's not one of these 4? Or would these 3 always be a subset of these 4?
I think it's a subset.
Yeah, they would always be a subset, because you're keeping the 4 most recently used
Always.
pages, and this is keeping the 3 most recently used. So, if you follow these in time, whatever 4 are here, without a doubt, I'm sorry, whatever 3 are here, without a doubt, those 3 plus an extra 1 would be here. So that scenario could never occur at least. So it depends on the algorithm, if, you know, to see if you can have this strange anomaly. The operating system's trying to help by giving you an extra frame, and it actually makes things worse. So, yeah?
The other thing was, I mean, I don't think this matters, but it wouldn't be in the same frame necessarily, though.
Yeah, it wouldn't be in the
It
same,
could
right,
not, that
but it
wouldn't
would be
change
in
anything.
memory. Yeah, it would be in a different location, but you would just go to your table and it tells you the
Yeah.
location, so it'll be there. And the big time-consuming thing is going out to the disk drive and bringing the page in. Obviously, you're processing on the processor. As soon as you have to go out to the disk drive, you're gone. You get back on the end of the list. You wait for something to come in from the disk drive, and then you have to go through the list again. So you want to try to avoid any of these exits. They're really time-consuming. Yeah.
How would the least used one work in this scenario? Because you have 4 and it goes like 4 back, you know what I'm saying? Like when you get to number 4, you have to pick between 0, 1, 2, and 3.
Yeah, so the least, if we're using least recently used, so really at any point in time, let's say we're at this point in time, and we wanted to pick which one, yeah, so these 4,
Like when you wanted to pick the 4, how would you decide?
when you wanted to put 4 in,
Yeah.
so you're looking at the most the recent past. You're saying, well, 1's been around, 0's been around, and 3's been around,
Okay.
and then 2. So you would kick 2 out.
Oh.
But yeah, what we were talking about before is, yeah, at the point where you're ready to bring in a new page, you wanna decide pretty quickly. You don't wanna say, like, I'm running an instruction from one page, now my next instruction's from a different page. You don't wanna spend a lot of time trying to figure out which one to kick out. The whole goal of making a good choice is to save time. So you don't wanna spend a lot of time figuring out which one to kick out to save time. But in order to implement the least recently used, we would probably somehow, we'd wanna say 1, 0, 3, and 2. Which of those is the oldest number? Which would be 2. We wanna have some kind of data structure that's keeping that in place. So kind of like a linked list, 2 points to 3, which points to 0, which points to 1. And here's the head of the linked list, and here's the tail. So you would kick this one out, and then put 4 at the end of the linked list, and now there's your new linked list. And just kind of moving through. But that means every time we even make a reference to a page, whether we have to load it into memory or not, every time we refer to a page, we have to update our data structure, and that takes time. So every operating system likes to use the recent past to try to predict the near future, but try to do it without taking up so much time. Okay, so